So now we do u of x1 z is equal to minus w from 0 to t, if you like, is equal to minus the integral. And now let me parameterize it straight away. From 0 to 1, s goes from 0 to 1. Oh, what's r prime s? It's equal to x, y, z. Alright, so I immediately write f evaluated at xs, ys, zs dot r prime s x, y, z ds. Alright, is equal to, what's f evaluated at this point? Well, f is constant. F is always 0, 0, minus mg, right? So I can just write this as minus the integral from 0 to 1 of 0, 0, minus mg dot x, y, z ds, which is minus mgz ds. Okay, so it's minus the integral from 0 to 1 of minus mgz ds. What's this? mgz, is it dependent on s? No. So this integral is just mgzs from 0 to 1. Which just gives me a value of, minus is cancelled, mgz. Exactly the same value. Are we surprised? No, because the work done is path independent, because we have a conservative force. So we've gone now along different paths, the green path. Green path and blue path give us the same answer. No surprises. That's because the force that we were using is path independent. So now you have the tools to compute these potential energies for any force, from any reference, along any path. And so you can compute the potential energy of anything. And you can tell me if it's conservative, and you can tell me the meaning of what I'm saying when I say a force is conservative. Also, when a force is conservative, remember that you can write down the ground gem for that force, L is T minus U, and then you can write the ground equation just by knowing U, which you're now able to compute, and T, which you were always able to compute. So we can compute this thing called L, and we can solve any system. So this bit, from here to here. Okay, so the force of gravity is 0, 0, and minus mg. It's not dependent on x, y, or z because it's the same as it. So when I evaluate it at xs, ys, and zs, well, there's no x, y, or z here, so it's always just 0, 0, and minus mg. So this goes there. If I put for instance, if I put an x here, it would no longer be a conservative force. If I did put an x here, right? Maybe it would be, I don't know. Then here, I would put a x. Right. And then the x, y, z is just what I was before. When I take the dot product, I get that, and then I do the integral. Right. So let me consider a problem that will make all of this stuff more useful. So far, all right, we can tell you whether a force is conservative, we can compute the potential energy, and that's great. That's lovely. That's wonderful. That's what we like. But what are we going to do with this? Here's an example problem that you might solve. In the classroom, we're obsessed with pendulums, so we'll look at a pendulum again. But this time, the pendulum is on some coil. There's a coil ordinary pendulum, but with one difference. It can spring up and down as it swings. Right? The spring is not allowed to bend. It's just allowed to go up and down, like a spring. And so my question is, and I'll leave this one for the tutorial, I suppose, because we are clearly at the tutorial level. My question is, can we compute the equations of motion of this thing, and can we use all the stuff that we've got above? Can we write down potential energies, and can we compute the equations of motion of the spring pendulum? How many degrees of freedom is that? The stretch length and the angle. So it's a 2 degrees of freedom problem. How many potential energies are we going to consider? Two. The gravitation and the spring potential. Right, we'll have to talk about the spring potential briefly, but we'll do it. Who here knows what the spring potential is? Alright, some of you, all hands are going up at all times. Well, okay, I'll do that before we close. I'll tell you what a spring potential is, and then we'll consider everything else in the tutorial. If I've got some spring, some object, right? So if you take the system and you just consider the spring, you don't consider the swinging and anything else, you just consider the fact you've got some string connected to the object, right? As I pull the string further and further and further away, it's going to give me more and more slack. I don't have a spring now as an example. Somebody who doesn't mind their hand being held when it comes to be a spring? I'm not that scary. Right, so you've got a bunch here. Right. Right. So here is a spring, and for instance, now the spring is very contorted. It's very easy to pull. As I pull harder and harder, now there's more resistance. As you can see, there's more resistance, and it's hard for me. And then as I go back, it's easier. Right. So as I go further away, it's harder. And as I go closer in, it's easier. Every spring has an equilibrium distance. And there's a point for her as well. So 1, 2, 3, 4 points today. Good. Right. So every spring has an equilibrium distance. The further away I go, the greater the resistive force. So let's say the equilibrium distance is here, x naught, right? If I push the spring in, it's going to push me back. If I pull the spring out, it's going to pull me back. So the force exerted by the spring on me as a function of x, the distance that I've stretched it, is proportional to the distance that I've stretched it from its equilibrium length in the opposite direction to the distance that I've stretched. The spring always pulls me backwards or pushes me backwards. So it's always in the opposite direction to the way that I've stretched. If I've stretched it all the way out to here, it pulls me backwards. If I've pushed it all the way to there, it pushes me this way. Convince yourself that this term will point this way over here and this way over here. And it correctly models the force exerted by a spring. Alright. We've got an equation for force. What's the standard thing to do once we've got an equation for force? Work out a potential, right? Work out potential. So we'll do that. The work done in bringing it from x naught. Now look, I'm just using x naught as my reference point because it's a nice place. This thing is symmetric about x naught. Remember, you can use anything as a reference point. So I'm going to be using x naught to a distance, to a stretch distance x, right? Is going to be, and I'll put a negative on there because I want the potential. A negative of the integral from x naught to x of consecutive integral from x naught to x of minus k x minus x naught dx. Let's change variables x minus x naught to u. Then this is going to be the integral where u goes from 0 to x minus x naught of minus k u du. U is equal to dx. When I integrate this, I think I've lost the minus here as well. When I integrate this, the minuses can cancel, right? There's no need to put the minuses. When I integrate this, I get a half k u squared evaluated between 0 and x minus x naught. So what's the spring potential? It's simply a half k times x minus x naught squared. Okay, so I have the potential function now for the spring. U of x is equal to a half k x minus x naught squared. And that will tell me everything by differentiating it with respect to x. Del u by del x, I get minus k x minus x naught. Oh, I get k. And if I put a minus in front of both, I get the minus. Remember, f of x is equal to minus del u by del x. Right, so everything works. We get the full state by differentiating. Our potential function is defined. We now know what the spring potential is. We know what the gravity potential is. We have all the power we need now to solve the problem of the spring pendulum, which we shall do in the tutorial. So the tutorial will start in, I don't know, whenever you guys are happy to start. Start now. They'll start when if we suggest we start, we don't get a resolution, and then we'll solve this one, and we've got one or two problems on the type as well in terms of finding a potential function. Right, let's have a short break.